When we say you've bombed in North America, we mean you failed. In England, when you bombed them, you did good. Oh, you're Comediac, you really bombed them, boys! So I want you to bomb this physics problem. The B-52 has been in service for 70 years. It's the world's largest bomber, and it will continue to be in service. It may be the first plane to reach a 100-year service life. It's been so versatile, and it came right after World War II. The Wright brothers' entire flight could fit on the wing of this thing. This thing can carry, a few of these planes can carry more weaponry than most entire wars in the past. When you drop a bomb from a plane, it's going to track the plane because Newton's law, that we'll get into next, says if there's no reason for speed to change, it won't. So from the viewpoint of the person in the plane, the bombs are following them. They're staying parallel. Even when the bombs have already had a few seconds to fall, you can see there's no drag yet affecting them. And in fact, one bomb seems to be so excited it's leaving the plane in what seems to be a preposterously wrong direction. It's probably the angle of the picture doing it. The B-52 has a service ceiling of 15,000 meters, and it can fly 844 kilometers an hour. This is not like World War I. These planes are so high up you could barely see them. And so there's going to be a significant time for those bombs to fall. All the while they're moving forward, only losing a tiny bit of speed due to wind resistance. Well, wind resistance doesn't kick until university. Though again, I want your personal best. So if you think you're ready to handle what's called Stokes' Law, I'll show it to you later. It's up to you. I would never hold you back, but I'm not going to force stuff on you. Step 1 would be to convert kilometers an hour to meters per second. What governs this equation? It's going to be how long does it take the bombs to reach the ground. That's the key to this one. Here are our knowns and unknowns. 15,000 meters, acceleration, and we don't know anything about the final speed or the time. We want the time, and the final speed's irrelevant. That would put this equation governing the situation. We can't use the V average T1 because we don't know final speed. Since the bombs start from rest, we can drop the VIT term. Now we rearrange to solve for time. We get this rearrangement, put our numbers in, we get 55 seconds. So it's nearly a full minute for those bombs to fall. The whole time, ignoring wind resistance, those bombs are continuing to travel 234 meters a second for 55 seconds. If I let you round that to 200 and that to 60 seconds, 6 times 2 is 12. 0, 0. You would get 12,000 meters by examination. 200 times 60 is 12,000. Let's put it in our formula. The distance is speed times time. That's 234 times 55 is about 13 kilometers. And your guesstimate, by rounding this low and this high, you get 12,000 meters. That's how easy it can be to estimate if you're willing to start learning how to do it. This is the zone around Orangeville, where I unfortunately live, that's 13 kilometers in a circle. And this means that once a bomber got within this black zone or right at it, it could drop its bombs and hit us. An anti-aircraft battery in Orangeville wouldn't even see, down by Forks of the Credit Park, the bomber. The bomber would drop its bombs, and a minute later, the town would suddenly start exploding, and you would never see the plane that did it. However, if the bomber doesn't drop his bombs until he's inside the circle, he will miss the town. So the bomber has a very narrow radius where they can drop their bombs given their wind speed, or they have to turn around and try again. I want to show you again how you can estimate and double check your answers, because you know I hated double checking. I won't do it, so I would come up with a different means. When you trust your calculator, you get 55 seconds rounded. But what if you wanted to see, could you actually estimate this in your head? And I'm going to show you, yes, you can. It is actually fairly straightforward to get in your head an estimate for this number. Just start my rounding game. Get rid of gravity as 9.8. It's stupid for most questions. This problem is going to be way off because of wind resistance. So I'm telling you, skipping wind resistance is causing far more change to this number than trying to be accurate with gravity. If you write it as 30,000 over 10, you can start doing math real easy. 2 times 15,000 is 30,000. Divided by 10 now, that's just the square root of 3,000. And you're like, I can't do that in my head. Of course you can't. Very few people can do a square root in your head. But you can do the opposite. You can go, I wonder what the square root of 3,000 is. Let's see. If I do 50 times 50, that's 2,500. And if I do 60 times 60, that's 3,600. So my answer should be somewhere between 50 and 60 seconds. Oh, I was right. And that's all it takes to ballpark. So you can actually calculate these things pretty close in your head. And when you ballpark it, it should be 50 to 60, and you see your calculator toss out 55, that is one heck of a confidence booster. You feel so much smarter when you do that. But this takes a willingness on your part and a long time trying this. But what it will really do is if you goofed and you forgot to hit the square root, or you did a times 9.8, when you get your estimate and your calculator spits out 0.001793, you suddenly go, that's not the correct answer. That's how I double check, not by repeating my math, because I will make the same mistakes. Other teachers, you'll really get pushed for significant digits. You can just go online and go, how do I do significant digits? It's a waste of our time together to teach you significant digits. It's not in the curriculum, and it is commonly done, but seriously, you could teach yourself on your own. My calculator gave me t equals 55.32, and on it went. And a lot of you really want to write down like 7 or 8 or 9 digits. But seriously, are they real digits in this problem? You might go, well, I'll just write time is equal to 55.33. And even that is wrong. I would just write 55 seconds. You don't need the rest. Teachers next year would tell you it's properly written 55.3. Why? Because gravity has the 0.8 in it. And if you write the 15,000 as 1.5 times 10 to the 3, you have a single digit. So they said you can have up to 1 digit. So depending on the method a teacher uses, you might be told 55.33, 55.3. But I think this is a waste of time teaching that part to you in school. If we don't look at the real world scenario, does this altimeter look to you like it could generate 15,000 feet to the exact mark? What about the newer digital ones? Digital devices are a lie. If I said to you, you need to be at exactly 12,000 feet with this altimeter, you'd go, geez, it's kind of crude. And if you then had a digital one, the digital one is actually no more accurate, except the mechanical one doesn't lie to you and say you're at 15,234.36 feet. You'll just look at it and go, it's a little over 15,000, but the digital one will give you all these decimal places. But these instruments all have error. And according to current regulations in the US, these altimeters, digital or not, only have to make it within a plus or minus 80-foot range. That's 24 meters. So when I said the bomber's at 15,000 meters, it could be at 15,024 or 14,076, plus or minus 24 meters from that. And if I calculate 2 times for an error in altitude, I get 55.28 or 55.33 seconds, which is outside the range of significant digits. So in a problem like this, the significant digits on your calculator have no real bearing in this. It's the instrumentation. You have to know how they're setting their altitude, and that is the key to the problem. And that's the stuff that I should be teaching you, how to understand where the numbers came from, not how many decimal places should I write. Because counting decimal places you can teach yourself. Understanding the nature of our instruments and how the data comes in is something that you need my help for. Let's now move on to another problem. Parkour or die. Having survived a Tide Pod challenge, Foolio decides to do a parkour jump between two buildings separated by 6 meters. Foolio's typical run has been measured to be about 4.25 meters per second. Can Foolio make the jump? Step 1, if it's not in the classroom, where did that number come from? How did Foolio get his speed? You must ask that, because sometimes people lie or they didn't know what they were doing with the device. So step 1, we need to identify the numbers that govern this problem, but we also have to be skeptical about that value someone's reported to us. Right? It is always possible you were given bad data. And we're not going to worry about Foolio's body shape. It doesn't matter that his feet are out here and then he's hanging from his hands. We're just going to treat him like a ball bouncing down. What is the key here? The key is exactly like the bomber, except Foolio is the bomb, in his own mind at least. When he jumps, his horizontal speed will just continue exactly like he was a bomb, but he will begin to fall. And by the time he's fallen to an altitude lower than the next building, he's done for. This will be the formula that governs him, exactly like the bomber. We rearrange and we get 1.42 seconds. Now what if we did Collatti's rearrangement and I let you do this? 1.41 seconds. That's the only change, 100th of a second using my estimation, and I was able to do it in my head because I'm old, I have no social life, and I know the square root of 2 is 1.41. We continue. We'll use my rounded time and the time where we didn't round gravity and see if it makes a difference to the answer. Foolio, we multiply his speed that he's running times the time that he has, and we get 6.035 meters. He just barely to 3 centimeters make it. That's the length of his fingers. And if we use my speed from rounding, we get 5.99.3. This means that in this case, my rounded number may actually change the answer from yes to no. If all we had to do is exceed 6 meters, then according to this, using accurate numbers, 9.8 for gravity, he made the jump. Using a rounded value, he did not make the jump. But in reality, dude, you're gonna die if you try this jump. So as a textbook question, it's quite clear if you use proper numbers, he made the jump. So here is my rounding causing a problem. Your yes-no answer would be messed up. Almost like I deliberately set it up to appear that way. But these are not the real world conditions. We have to look at these numbers in the real world to actually go, does Foolio have even the remotest chance of making this jump? Let's suppose Foolio used the police radar gun to get the speed he ran. Those police radar guns are plus or minus 2 kilometers an hour. How do I know that? Just Google it. Just pick an instrument and go, what is the accuracy or precision of this device? You'll be surprised to find out how inaccurate many devices are, even though they have lots of decimals on their display. And this is just the instrumentation to use. Right? We got 0.5 meter a second on the instrumentation alone. But how consistent is Foolio? Let's suppose he wants to measure his running time on some event, and he gets 30. You know, I know this says like 29 in here. Let's call this 30. And he consistently runs the time in 30 seconds, and you notice very little drift from that time. But what if Foolio's running speeds have been mapped out like this? You get an average here, but you might go, dude, you're really slow a lot of the time. You don't consistently come in at the speed necessary for the jump. That's real world, and that could make all the difference in this being just luck that he makes it. So when people say we calculated, and I'm like, no, you calculated it was at work, but you were just bloody lucky he made the speed today, because he's quite frequently not running that speed. And this is the part of error analysis that takes thinking. Like the poor stuntman that thought because he timed the burn of a rope once, he would get that time every single time he tried. So looking at the design of an experiment to me is more important than significant digits in terms of my participating and educating you. So let's build in Foolio's error from the police radar gun. We're going to take a speed and add to it the error of the radar gun and subtract, run the problem again, and see if he consistently at the range that instrument recorded, if we're safe. So Foolio might have been running 3.7, he might have been running 4.7. And if we put those numbers in, he'd be Foolio now, brah. At the lower speed range, he isn't even going to come close to making the jump. So he'd be Foolio. But another problem comes in. If he succeeds in actually running faster, he could jump almost 7 meters, but dude, he's Flatio now. He's going to be injured. And why I say he be Flatio? Simple. Everybody thinks that when you run horizontally, you magically defy gravity. You run off this, you start plunging. And you might go, well, I don't know, maybe if he really ran fast enough. If I shove the two buildings together and say, hey, you want to jump 10 meters? You saw what happened to that girl when she jumped like 2 meters. And she landed with her legs out and buckled at the knees immediately, and she still broke her legs. She didn't land straight-legged. She collapsed like you would expect, and she ruined her legs for life. So this is a 10-meter fall. You're not walking away from it. We go, how fast is he actually going to hit? He hits at 50 kilometers an hour. Just try to imagine your parents are driving down the street at regular street speed and you leap out directly into a telephone pole. You're not walking away from this. With really careful landing technique, when he jumps, he's actually going to be traveling faster than 14 meters a second because he's adding his running speed to the drop. And that puts him at like just a smidgen over. He might tumble and roll. But all the records I've looked up, nobody has done a parkour jump higher than 7 meters without injury. And that girl only jumped like 3 meters, and she will never walk properly again. And even if she gets 20 good years on her legs, when she gets to be my age, those injuries are going to come back. The last problem is training for a jump. A daredevil plans to jump a motorcycle between train cars. A 30-meter gap exists by using a flatbed car, 27.29. We're going to use some decimal places this time. And the width of these cars is 3.3 meters. Ignore the fact that train cars, just because this car is 27.29 meters, I know there's a couple of meters on either end. Let's just pretend it ain't there. So he's going to jump the gap when it comes through. We are going to pretend that this is a flat world problem. Almost like the train was totally level with the road, so he's not jumping the motorcycle. That gets to grade 12. We just need to know the speed he needs to be on the horizontal to shoot through that gap just as the train comes by. So how do we decide to help him plan his thing? How do we get the physics going? So the distance the train travels and the distance he's traveled, they meet up perfectly at the same point in space and the same time in space. Once you spot it, then we're really only in grade 8 math. I'm going to label the center of the train car with this X. And I'm going to tell you the train speed is 50 kilometers an hour and the motorcycle is 120 kilometers an hour. And that narrows your search for you. You could make up your own examples, though, after this. And I'm telling you, we want him to take 10 seconds to get there. I picked 10 seconds arbitrarily. I could have said 3 seconds. I could have said 30. But I think 10 seconds is good enough for a drum roll to get the crowd pumped and go, watch what we're going to do. This now lets us plan the distance of the train and the distance of the motorcycle when the problem starts. And we need them already at speed. We're not putting any acceleration into this. Right? The train would have had to start miles ago, and the motorcycle can come up to speed so fast, it's not a big deal. We just want to know when they enter the problem where the crowds are at these two speeds, how far back will they be for a total intersection. The motorcycle has 10 seconds to travel at 120 kilometers an hour, which gives us 333 meters. So the motorcycle starts 333 meters back from this. When we do the same for the train, 10 seconds times the train speed, we find the train would have to be set back 139 meters. However, this is where you got to be really careful. We've set the distance of the train from the front end of the car. We need to make sure he passes through the center. If we let him jump just as the train's completed 139 meters, he's going to smack his head on the back of the last boxcar. So we want him to reach the train when the train's center has passed. So if we take the train back 139 meters, it will just be at the gap. So we have to subtract a bit of distance from the train. We got to scoot it forward half its length to make sure that it's the center line he intercepts. So the train has to start 125.4 meters away and the motorcycle 333, and he will intersect the center. The final consideration, when he begins his jump, the train is still moving. So the train is going to move forward in the time he's jumping the width of the train, 3.3 meters. Now, he is traveling 33 meters a second, and by sheer dumb luck, these trains are 3.3 meters wide. How convenient is that? You are traveling 33 meters a second, and you're clearing a gap of 3.3 meters. This is going to be fast. I bet you he's totally safe. The time for his jump is the distance he's jumping, dividing by his speed. He only needs 1/10 of a second to clear the train. How much can the train move in that time? Well, we take this time, we put it in here with the train speed, and that's easy, dude. He's only lost a meter. He's totally safe. The train's not moving remotely fast enough to have him enter the gap only to be clocked by the next boxcar. Good. So we've got ourselves a scenario. Both him and the train, a couple hundred meters back. He's got plenty of clearance. Now we got to go to those pesky instruments. What happens if he's too slow? What happens if he's too fast? What are the margins for error for this guy to make it? Can he be 25 meters a second and enter the jump? Can he be 40 meters a second and still make it? Because if he comes in too fast, he's going to slam into the train in front of the flat car. If he comes in too slow, he's going to hit the rear one. So we want to know what's his limit of wiggle room to make the jump. The time for 13.6 meters of the train to pass, and that's all we need to know. The train's moving at 13.9 meters a second. How long for the train to move half of its length? And we get 0.97 seconds. You don't need to calculate it for both. If he's fast by 0.97 seconds, he will slam into the boxcar in front, the blue line. If he's slow by 0.97 seconds, he will slam into the boxcar on the other side. How much is that on a speedometer? That he does this race 1 second too fast or 1 second too slow? First of all, you're already going. He needs to run 1/3 of a kilometer in 10 seconds. And we've already calculated he can only be off that time by 1 second up or down, and he will die. Does this sound yet like this jump is doable. We want him to complete the run in 120 kilometers an hour, taking 10 seconds. This determined that he would start 333 meters away. But what if his time is wrong? If he is off by 0.97 seconds, either way, he will arrive too early or arrive too late and hit a boxcar. So if he does 330 meters in 10.97 seconds, he will be at this speed. If he does the race a second too fast, he's going to reach this speed. And he's supposed to be at 33. This makes the low speed 109 and the high speed 133 when he should be at 120. That's what it looks like on the speedometer. He must keep his speed between the red and the blue line or he's dead. But even more ominously to me is this notion that he has a 1 second error in 10 seconds. And if he's more than 1 second off, or just a second off, fast or slow, he hits. Would you provide this man with a recommendation of doing this jump? Or do you think this is unnecessarily risky given these numbers? And I wish more stuntmen would do these calculations before they just guessed. Then you can watch this. So those are about the most difficult problems I could imagine giving you. But the train one, you got to realize there was very little math there that you couldn't handle. It's all simple. It's just coming to the decision making that is the real hard part. And that's what I want to focus on with you, so you know where to start a problem rather than going, oh, the teacher's going to give us every possible example. Well, you don't learn how to think if you just have, we didn't do an example like that.